Alright, let's move forward. I'm going to start talking about partial derivatives. I'm going to get into integrals and stuff like that because we really haven't gotten into the vector calculus part of this vector calculus playlist. Been talking a lot about parameterization and all that kind of stuff, which is important, and we'll come back to it later, but let's start moving forward, and we'll start talking about partial derivatives, and then I'll get into like iterated integrals and that kind of stuff. And today I'm not gonna spend too much time on partial derivatives because they're basically just like derivatives that you would have taken in first year. I'll explain them just a bit, but then I'm going to jump right into like an application of partial derivatives, which is the gradient vector. Okay, so quickly, let's say that we have some surface. Okay, so like this is one of the octants of this three-dimensional space here, and this is where the surface crosses the xz plane. This is where it crosses the xy plane. This is where it crosses, or this is where it crosses the zy plane. And this is where it crosses the xy plane. Okay, so the surface is like bulging out towards us, sort of like that. Okay, so partial derivatives are just like normal derivatives. Okay, they tell you the rate that a function is increasing, but since say z is a function of x and y, you might want to know how fast this function is increasing in the x direction, and then you might want to know how fast the function is increasing in the y direction. So let's say we hold y constant. Okay, and we look at a little slither of this graph like that. Okay, I just changed the color of the curve there. So let's say that we're looking at a little slither of this function, and we're interested in how fast the function is increasing right there. So if you were to take the derivative in the x direction at this point, you would have the slope of a tangent line that just touches the curve at that point and is parallel to the xz plane. Okay, so similarly, if we were to hold x constant along this little slither of the graph, then we would have the slope. Of a tangent line that's parallel to the zy plane and has the slope f sub y. So this has the slope f sub x, which is the partial derivative of f with respect to x. This has the partial derivative of x with respect to y, like that. Okay, so I know that was sort of a rough little explanation, but it's pretty straightforward. So I'll just show you a quick example of taking a partial derivative. So let's say that we had some surface that was a function of x and y. Let's just say that it was x squared plus y squared. Well, if we wanted to know the partial derivative of f with respect to x, then you act like y is just a constant number. Okay, it is a constant number. You're holding y fixed at a certain point. So here, when we took the derivative in the x direction, this tangent line here, the slope of this tangent line, derivative of f in the x direction, we held y constant. So when we take the derivative of f with respect to x, we treat y as if it's just a constant, and then we just take the derivative of the function with respect to x like any other derivative. Similarly, if you were to take the derivative of f with respect to y, we would hold x constant, which is what we did here. Okay, this is just some value of x, and this is just some value of y. We held them constant. They're not varying, only x is varying. So this would be the derivative of f with respect to x, and this would be the derivative of f with respect to y. So I'll just show you one more example. If we had f of xy, and it was x squared y plus y squared x cubed, then the derivative of f with respect to x, okay, so we're taking the derivative of this guy with respect to x. Y is just a constant, just like a constant number. So if we were to take the derivative of this term here, we'd have 2x, and then, if we were taking the derivative of 4x squared, then the derivative of that guy would be 8x, right? So we multiplied in this constant term here. Well, that's similar to what we do with y. It's not similar, it's exactly what we do with y here. And then we have to worry about this term here. So again, y is just a number, and then we take the derivative of the x term here. And then again, whoops. So this time, x is just a number. So if we were to take the derivative of like a y, where a is just a constant, then the derivative of that would just be a, right? Well, same with here. The derivative of x squared y with respect to y is just x squared, and similarly over here we have that. So I think you get the idea. So I'm going to move on to what the gradient vector is now. Okay, so if we have some function, let's say that z is some function of x and y, then the gradient of this function, which is denoted as this vector operator del here, which acts on f, and all it is the derivative of the function in the x direction multiplied by a unit vector that points in the direction of x, plus the derivative of the function with respect to y times the unit vector that points in the y direction. Okay, so watch this. Wow. Okay, so I'll just show you a quick example, and then I'll explain what the gradient is. Okay, so it's a vector, and it's related to these rates of change. Okay, so obviously it's going to tell us something about how fast x changes in each direction, and it's going to be, obviously it's a vector. Okay, so a vector points in some direction, it has some magnitude. So perhaps you could probably guess that the gradient of a function is going to be some vector that points in a particular direction that's related to maybe how fast the function is increasing or decreasing or something like that, right? So let's say that we had a function f of xy equals, let's say, sine xy plus e to the xy. Okay, so if we wanted to know the gradient of this guy, okay, at a point, right? Remember, this is evaluated at some point xy, and then these are all evaluated at some point xy. So everywhere on the function f, everywhere on that that surface or whatever it may be, there's going to be a vector that points in some direction. Okay, so here the gradient of f is going to be, well, let's do it. Okay, so here we'll have to use a chain rule. So we take the derivative of the outside of this, so cos xy, and then what's the derivative of the inside with respect to x? Okay, so the derivative of the inside with respect to x is just y plus, so now what about this guy? Again, we have to use the chain rule again, so we take the derivative of the outside, which is e to the xy, and we multiply by the derivative of the inside. Okay, So there's the x component of this gradient vector. And let's do the same thing for y. And it's, there's like some symmetry here, whatever you want to call it. So it's going to look similar to what we have on the other side. But when we take the derivative of the inside function here with respect to y, we're going to end up with the x on the other side, which is what I have here. Okay, so there's our first gradient vector. So now, before we start looking at gradients more closely, I'm just going to tell you a couple things. Okay, so let's say that we have some surface that sort of like looks like this. Okay, so maybe it increases over here somewhere, crosses the z-axis right there at some value. So this is going to be, again, function of x and y. Okay, so let's say that we wanted to find out what the gradient of this function was right at that point right there. Okay, so at some y value and at some x value. Okay, well, let's take a look again what the gradient would be. Okay, so it'd be the derivative of the function with respect to x, pointing in the direction of the unit vector that points in the I direction, and the derivative of the function with respect to y that points in the direction of the unit vector that points in the y direction there. Okay, so what does this mean? So, right there and there are our unit vectors. There's j and there's I. Okay, so the reason I drew this function, curled up like this, was to hopefully show you that, just to give you some intuition about what this gradient actually means here. So you can imagine that this function is increasing pretty fast, sort of like as you move back in the negative x direction. So maybe we could say that, just by looking at this random surface that I drew here, that maybe we can see that as x varies from 0 in this direction, you can see that this function is decreasing, right? So that sort of tells us that perhaps the derivative with respect to x of this particular function is going to be negative, right? Because it looks like it's decreasing as you move in the positive x direction. So it's kind of hard to tell maybe what the function's doing in the y direction, but let's just say that maybe it's increasing. Okay. What else can we sort of tell by this? It looks like it's increasing pretty fast in that negative x direction. So maybe negative f sub x maybe it's a lot bigger than f sub y, right? Just by looking at how I drew this here. So what would the gradient vector look like in this case? Well, if f sub x was negative, okay, then it means that f sub x is going to, we're going to multiply the I hat by f sub x, which means that we're going to have like a component of our gradient vector that points in the negative I hat direction. Okay, and if actually maybe I should write this like this. Maybe like the absolute value of f of x is a lot bigger than f sub y. So that means that if the absolute value of f sub x is a lot bigger than f sub y, that means that maybe we're going to have some component to our gradient vector that points like this, and then maybe in the y direction, who knows, maybe it's only that big. Okay, let's make this a little bit bigger. Okay, so that's f sub x. I hat. This is f sub y, j hat. Okay, so that means that the gradient vector would be, like the sum of these two vectors. So like grad f would look something like that, or the gradient of f would look something like that. So you can see here that it doesn't have any z components. For this three-dimensional surface, it doesn't have any z components. So it's like this, it's parallel to the xy plane. And you can see that the direction that the gradient vector points in is in the direction of the greatest increase of this function. Okay, so I'll show you an example here in a minute what that means, but before we get too far into it, I'm just sort of trying to hopefully convince you guys of a couple properties of the gradient vector. So I just want to talk about one more. Oops. And I'll show you some examples and stuff like in the next video and later in this video. I'll plot some stuff in MATLAB. Okay, so here we have another surface. Okay, maybe it's some sort of paraboloid that is revolved around the, that has the x-axis like through its center like this. So this function would have an equation that looks something like this, right? So let's pick different values for z and see what we get here. So like when z is 1, what do we have? We have a circle like this. When z is 2, what do we have? We have a circle like this. So you can see that at different values of z, we have these different concentric circles there. So maybe that's when z equals 1 and we have this circle. Okay, maybe that's where z equals 2 and we have this other curve. So these are level curves, right? And if we project these down into the xy plane, then what do we have? We have these concentric circles for, oh my god, terrible drawing, for all these different values of z, right? Well, one thing that I'm going to show you later, I'm going to tell you right now, but I'll actually prove it in like the next video or something, is that if you were to take the gradient of let's say this function, let's say like right here when z equals 2 and x and y equal whatever their corresponding values are, if you were to find the gradient of z at that point and then you were to sort of plot that gradient vector on the level curve where z equals 2, you would see that where z equals 2, you would see that the gradient vector is actually perpendicular to the level curve. Okay, so the gradient vector is perpendicular to the level curves of a function. Okay, so I'll show you that here in a sec. Actually, I'll show it to you right now. Okay, so here we are in MATLAB. Here is a paraboloid that's been shifted up by 0.25 so that we can see the xy plane below it. Okay, so what we have right here is our paraboloid. Okay, like a three-dimensional parabola. Down there on the xy plane, you can see level curves for different values of our functions. So at different values of z, plotting the projection of that corresponding level curve down onto the xy plane. And then each of those arrows are gradient vectors at different points at different xy values along the this curve here. Okay, so let me just step out of this for a minute. I'm going to shut off the plot of the function. We'll just look at the level curves and the gradient vectors. Okay, so you can see that right here, for example, here's a level curve I don't know which level curve it is. I don't know what z equals in this case, but you can see that the gradient vectors like are perpendicular to this level curve. This one looks like it's not, but you can see that it actually starts a little bit before. But let's pick one. Okay, so that one there looks like a good one. Looks like that gradient was calculated pretty much right where that level curve is. So you can see that it's perpendicular to the level curve at that point. Let's look at this guy here. I'm just going to change the axis a little bit. Okay, I'll post this code somewhere, a link to it or something like that. Oops, let me show you what the surface looks like. Okay, so here we got a pretty neat looking surface. You can see that it, if you were to start, say these are like mountains and these are like valleys or something. If you were to start right here, you could see that, like, if you traveled in this direction, that you'd be increasing pretty rapidly. If you started right here and you sort of went this way, you'd see that you'd be decreasing pretty rapidly. Okay, so let's just see how that corresponds to the gradient vectors, like what I talked about earlier, about how they point in the direction of increase. Okay, so let me plot some more gradient vectors here so we can see what's going on. Okay, so like I said, so these are the level curves. So I shut off the actual graph of the surface. So like I said, if you were to start here, let's zoom in. Oops. You can see that the gradient vectors are pointing in the direction of pointing in the direction that this function increases. I don't know if that's good English or not, but so you can see that, like, this is where the function was red, where it was up high. You can see that the gradient vectors are pointing to where the function was increasing. So here, these circles here correspond to the bottom of this valley here. If you were to start at the bottom of that valley and you sort of like walked towards us here, you'd have to climb up out of that cliff. So that these gradient vectors there are showing you like where it's increasing, and it's actually showing you how fast it's increasing, right? So down at the bottom, it's where it's steepest, so the magnitude of the gradient vector is longest down there, and then as you get up to the top surface, the magnitude of the gradient vectors decrease because it's not as sharp, right? It's not as steep. And if that's flat, if you were to take the derivative of some function that was flat, you would see that the rate of change in that direction would be 0. So that's why the magnitude of these gradient vectors are decreasing along this at the top here, and then where it's flat. So like right here, this white space where you don't see any gradient vectors, perhaps that's where the function is flat, right? So it's not increasing or decreasing there. Right? So that makes sense. And then one more quick example. Okay, so this guy looks pretty cool. So this is the normalized form of sine x over x. Okay, so you can see right there. Oh, it's been shifted up by 0.5 just so that I could make some space underneath the surface to see the contour plot and the gradient vectors. But so you can see that this function is steep right here, increases pretty fast, and it has this little bit of a ripple effect here. And like if you were to extend this axis beyond, you'd see more ripples. So it looks sort of like like a rock was dropped into a pond here or something. And if you were to take a snapshot like right after impact or something, right, it looks pretty neat. So now let's shut off the surface and look at the contour plots. Okay, so like I said, in the center is where it was steepest. So you can see that the magnitude of the gradient vectors are quite long, reflecting that. Okay, and they point in the direction of the like the fastest increase of that function. And then, like I said, when you move away from the center, there's like this little ripple effect, right? So you can imagine like we're moving down that steep hill, right? We get to this little part here where the function is flat, and then it starts to increase again right here. You can see the direction of the gradient vectors are pointing in this direction, which means that the surface must be increasing right here. And then you can see that right at the top, maybe that's right at the peak where the function's flat again, and then it starts to decrease again. Right? So these gradient vectors are telling us to go back because it's the direction that the function's increasing. Right? So you can sort of see the ripple effect there and how it relates to the gradient vectors. So hopefully you get an idea of how the gradient vectors tell you, they give you an idea of like the rate of change and which direction is the fastest rate of change of some surface. And hopefully you believe me that gradient vectors are perpendicular to level curves, because we're going to use that information later when we try to linearize surfaces, like linear approximations or tangent plane approximations and stuff like that, because yeah, gradient vectors can be useful for that kind of thing. So I'll probably do that in the next video or the video after that. So anyways, thank you very much.